Faraday's law of electromagnetic induction states that a change in magnetic flux over time can induce an electromotive force. So this can be written as an instantaneous quantity, or the average electromotive force generated from a finite change in magnetic flux. So for example, if we consider this conductor on a rail, so it completes a circuit, and this rod moves in a magnetic field at a constant velocity. So if we label the position of the rod as x, and this length as y, then a magnetic flux is the magnetic field which is going into the screen, or the negative x direction, multiplied by that area. And therefore the change in magnetic flux with respect to time is equal to b times y, which are constant because the rod is moving in the x direction. So therefore we have by dx dt. And the change in position of the rod with respect to time is the velocity. And the polarity of the electromotive force is determined by Lenz's law. So an induced EMF generates a current which creates a magnetic field that opposes the change in magnetic flux. So in other words, because the change in magnetic flux is going into the screen, then the induced current, being I, must act in a direction that produces a magnetic field that points out of the screen. So adding Lenz's law to Faraday's law, we put a negative sign behind the change in magnetic flux. So the direction of this current is determined by the right-hand rule to produce an opposing magnetic field to the change in magnetic flux due to the motion of this rod. So remember that the magnetic force is equal to the current by the length vector crossed with the magnetic field. And this length vector is in the direction of the current, and a magnetic field is going into the screen. So L cross B will produce a magnetic force in this direction that acts to oppose the motion of the rod. So that's why this addition is important, because if the current was flowing in the opposite direction and created a magnetic field that amplified the change in magnetic flux into the screen, then this force would act to the right, because the magnetic field created by the induced current would basically magnify the change that produced it. And in that case, energy would not be conserved, and the rod would just keep accelerating to the right, to infinity. So therefore the EMF, due to the change in magnetic flux, is equal to minus B by Y by V. Suppose we have a solenoid that's produced with loops with n number of turns, and we have a wire that has an electric current flowing upwards. So as we know, the magnetic field produced by this wire has a magnitude of the magnetic permeability by the current on 2 pi by the radial distance away from the wire. And by the right hand rule, the magnetic field lines will flow anti-clockwise. So if we consider this solenoid going along the y-axis, and we look from the y-axis, then we see one of the loops as follows. So the magnetic field produced by this wire is going to cause a magnetic flux through a loop of the solenoid going out of the screen. And here we assume the area of the solenoid is small compared to the distance from the wire, so the magnetic field through a loop of the solenoid is uniform. So for this solenoid with n number of turns, Faraday's law states that the EMF is equal to minus the number of turns multiplied by the change in magnetic flux through a loop of the solenoid with respect to time. So if this current in the wire is steady, then that won't produce a change in magnetic flux through the solenoid. So the magnetic flux through the loop, where the loop has an area A, is equal to B multiplied by A, which is mu naught by I on 2 pi r by A. So therefore we can write this expression as minus n multiplied by A, which is constant, by mu naught on 2 pi r, which are also constant, multiplied by the change in current with respect to time. So if the current in this wire is steady, then there won't be an EMF produced in this solenoid. So if we suppose this current is not steady, so for example it's increasing with time, so that's going to result in a magnetic flux out of the screen that's increasing. So therefore the EMF produced in this solenoid by the right hand rule is going to result in a magnetic field that points into the screen to oppose that change in magnetic flux. So the current in this solenoid is going to flow clockwise. So effectively we take advantage of the right hand rule to determine the relationships between the current, electromotive force, and magnetic flux. And note that using SI units, the units of EMF will be in volts. If we have a conductor moving through a magnetic field at some velocity, then the magnetic force being equal to the charge by the cross product between the velocity and magnetic field vector is going to act on the charges inside that conductor, which are now moving. Now for a magnetic field acting into the screen, or the negative x direction, if we take the cross product between these two vectors by the right hand rule, the magnetic force will point upwards. So this direction of the magnetic force is the direction that it acts on a positive charge. So therefore for a negative charge, the force acts downwards and pushes electrons to the bottom of the wire, leaving behind positive charge on the wire, and therefore that results in an electric field. pointing from the positive to the negative charge, which is uniform. So therefore the change in electric potential is the potential at the positive charge minus the potential at the negative charge. So this is the voltage, or change in electric potential, or the EMF, which is equal to the electric field by the length of the wire. So therefore when electromagnetic equilibrium is reached, where the electric force on a charge is balanced by the magnetic force, we have the charges cancelling, and we can write the electric field as the speed of the conductor by the magnetic field by the length of the wire. Now consider this wire with a changing current, which results in a changing magnetic flux going out of the screen through this loop of wire. And according to Faraday's law, a changing magnetic flux is going to produce an EMF that opposes it. So in other words, the current flowing through this loop is going to be clockwise, resulting in a magnetic field going into the screen. But given this loop of wire is stationary, the magnetic force could not have possibly caused this flow of current through this loop of wire, because the charge is not moving in the first place. So therefore, an electric field must have been induced by the magnetic field that produces an electric force to push that charge along that loop of wire. So effectively, an electric field must have been induced by the magnetic field. And the work done by the electric force to move the charge around the closed path can be written as a line integral. So that will be the integral over the closed path of the dot product between the electric field and the differential length vector along that path. So Faraday's law is restated that a changing magnetic flux induces an electric field, and the work done by the electric force per unit charge around a closed loop is equal to the electromotive force, or EMF. So this is Faraday's law of induction, which is Maxwell's third equation. That describes the relationship between a changing magnetic flux and an induced electric field. An electromagnetic wave, or a light wave, consists of oscillations of an electric field and a magnetic field. And these don't require a medium to propagate, so they travel at a constant speed in free space. So an example are light waves from the sun, and we can see the sun from the earth because these waves can propagate through free space before they reach earth. So we can generally use Maxwell's equations to derive the wave equations and show that electric and magnetic fields obey these equations, but this requires that you take Calculus 3 to understand the partial differential equations. But basically the speed of light is derived from the wave equations, that can be derived from Maxwell's equations, and you'll see that the speed of light is 1 over the square root of the magnetic permeability of free space and the electric permittivity of free space. And just to show some numbers, the permittivity of free space is 8.854 by 10 to the minus 12 coulombs squared per Newton meter squared. And the magnetic permeability is 4 pi by 10 to the minus 7 Newton per square ampere. And recall that an ampere is in coulombs per second, so ampere squared will be in coulombs squared per second squared. And if you substitute these values, you get the speed of light is approximately 3 by 10 to the 8 meters per second. And you'll be able to do the derivation and connect Maxwell's equations with physical phenomena when you take more advanced physics courses. A rectangular loop is placed at a distance d from a long wire, which carries a current as shown. Now if the current is increased at a steady rate from I1 to I2 over time t, find the magnitude and direction of the current induced in the rectangular loop. So as we know, the magnetic field due to a long wire has a magnitude of the magnetic permeability by the current in the wire on 2 pi by the radial distance from the wire. And the direction is determined by the right hand rule. So given the current is going upwards, then the magnetic field line will be anti-clockwise. So at some distance x from the wire inside that loop, the magnetic field is going to point out of the screen, and it's going to be the same at all points along this yellow line, because it has the same radial distance from the wire. So if we cut out an element of width dx from the area of this rectangular loop, then we can find the magnetic flux acting on this element. So the differential magnetic flux acting on that element of area is equal to the magnetic field being mu naught by I on 2 pi by the distance x multiplied by the area of that differential element, which is the height of the loop, by dx. And to get the total magnetic flux on this area of loop, we integrate both sides. So here we're integrating from d to d plus b. So we get the total magnetic flux on that area by evaluating this integral. So taking the constants outside, we have mu naught I by h on 2 pi. And then we're evaluating the integral of 1 on x, which is the natural log of x, from d to d plus b. So that gives a total magnetic flux of mu naught I h on 2 pi by the natural log of d plus b on d. So therefore, the electromotive force induced in this rectangular loop is minus the change in magnetic flux over time. So that gives minus, and the only quantity in a magnetic flux that depends on time is the current, which gives the I dt. And the problem states that the current is increased from I1 to I2 over time t at a steady rate. So this derivative, being the change in current over time, is the final current minus the initial current on t. So because the current in the wire is increasing, that's going to result in a magnetic flux that's increasing out of the screen. So therefore the current in this loop is going to act to create a magnetic field that opposes the change in magnetic flux. So by the right hand rule, the current flows clockwise to create a magnetic field going into the screen. And the magnitude of the current is obtained if we assume the resistance of this loop of wire is R. So remember, by Ohm's law, the voltage is equal to the current by the resistance. So here, the voltage is the EMF induced in this loop of wire. So we have the current is equal to the electromotive force on the resistance of the loop of wire. So we'll just divide this expression by R, and we can take the absolute value to get the magnitude of the current. A solenoid has a radius Rs and is surrounded by a circular loop of wire with a radius of Rw. If the current in the solenoid is increased at the following rate of I' of t amperes per second, what is the magnitude of the induced electric field at each point along the wire? And we can assume that the magnetic field only exists inside the solenoid and points into the screen. So it looks something like this. So recall that Faraday's law states that the work done by the electric force per unit charge along a closed path is the integral of the dot product between the electric field and a differential length vector along the path, which is equal to minus the change in magnetic flux over time. So a change in magnetic flux induces an electric field. So the magnetic flux through this loop of wire is equal to the magnetic field created by the solenoid, which is a magnetic permeability, by the number of turns in the solenoid per unit length. So we're only looking at a circular wire, so that's why we use the number of turns per unit length, as we want the magnetic flux through the thin loop of wire. And that's multiplied by the current in the solenoid, and we multiply this by the area through which it's acting. So the magnetic field only exists inside the solenoid, so it's acting through the area pi by the radius of the solenoid squared. So therefore the negative of the change in magnetic flux is mu naught by n by pi by the radius of the solenoid squared by the rate of change of the current with respect to time, which is I' of t. So given that the current in the solenoid is being increased, then that's going to cause an increase in magnetic flux into the screen. So therefore the current in a loop of wire is going to be anti-clockwise by the right hand rule to produce a magnetic field out of the screen which opposes the change in magnetic flux into the screen. So therefore the electric field is going to be tangent to this loop of wire, resulting in an electric force that effectively pushes the positive charge anti-clockwise around the loop in the direction of the conventional current. So therefore the electric field vectors are always in the same direction as the differential length vectors along the path. So therefore this integral evaluates to E by the length of the circular path, which is 2 pi by the radius of the wire. And we're asked for the magnitude of the induced electric field, so we take the absolute value, getting rid of this negative sign. And given that the current in a solenoid is increased at this rate, then this value is positive. So dividing through by 2 pi by the radius of the wire, the pi's cancel, and we obtain a magnitude of the electric field as mu naught by the number of turns in the solenoid per unit length, by the radius of the solenoid squared, by the rate at which the current is increased, over 2 Rw.